Hi everyone. In these videos we're going to be looking at Chapter 13. So before we start, I want to just get into what we're going to be looking at in Unit 3. So we've learned how to collect data and calculate statistics. We know what it means for a sample to be random and how to take good samples. So what does it mean when we take a good sample and we collect statistics? What can we then say about the population? So making inferences about the population using a sample is called inferential statistics. And that is what we're going to be studying in Unit 3. So we're going to start by examining patterns in the samples if we know the population parameter. So basically, we're going to start off by kind of looking in the back of the book and looking at the answer, and then looking at the patterns that got us to that answer. Then we're going to use those patterns to then make confidence intervals and discuss why we're allowed to do that. We use those patterns to do that. Then finally, we're going to conduct hypothesis tests. So in this unit, we're going to be looking at two different types of sampling distributions, one for proportions and one for means. We're going to be looking at 5 different types of confidence intervals, but they're going to be based on 2 types, one for proportions and one for means. And then we're going to be looking at 7 different hypothesis tests, again, based in one that is for proportions and one that is for means. So there is definitely a pattern to everything that we study in this unit. So starting off with Chapter 13, we're going to look at proportions. We're going to start off by looking at sampling distributions for proportions, and that's that idea where we know what the population proportion is and we're going to look at the patterns, and then we're going to use that pattern to discuss confidence intervals. So this page, I just want to talk about the notation and make sure that we all have the same notation and the vocabulary that goes along with it. So when we talk about a population proportion, we use a p, just a plain lowercase p, to talk about a population proportion. A sample proportion uses a p hat. And that p hat we find by making a fraction of x over n, where x is the number of people that have a certain characteristic and n is the entire sample size. So for example, let's say we have a computer retailer wants to estimate the proportion of people in her city who own laptop computers. She can't survey everyone in the city, so she draws a sample of 100 people and surveys them. It turns out that 35 out of the 100 people in the sample own laptops. So this means that the sample proportion, p hat, is 35 out of a 100. And that 35 is considered the x, the number of people that own laptops. And n is the sample size, 100. Where the population proportion is the proportion of people in the entire city that own laptops. So the question is, if we have this single proportion, 35 out of 100, what does that tell us about the population proportion? Is it also 35 out of 100? Probably not. So remember when we did simulations and we would have multiple people run a simulation in exactly the same way and get slightly different answers. And we had simulations that use proportions, right? What's the probability of, I forget what are some things that we had, but it was, we were finding the proportion of some kind of success. And some people got very different answers than other people, but nobody really did anything wrong. It was just called sampling variability. Sampling variability is completely natural and normal and doesn't mean that there's anything incorrect happening. So if we have this population and then we're gathering all of these p hats, then that means that since these sample proportions are different, that they then create a probability distribution, or we call it a sampling distribution of p-hats. I have a video, an example video, where I show like the population proportion, and then there's an applet that gives a whole bunch of different p-hats and the pattern that's happening with that. Definitely check that out. But for the sake of these slides, I'm going to use an example. So we have an example where we're tossing a coin 5 times, which means that our sample size each time is 5, or n equals 5. And we're going to let p hat be the proportion of times that the coin lands on heads. And we also know, because of probability, that the probability that the coin lands on heads each individual time is 0.5. So we know the population proportion. The population proportion is 0.5. We want to look at all the different possibilities for the sample proportion. So for example, we could toss a coin 5 times and not get any heads, and then our proportion would be 0 out of 5. Or we could toss a coin 5 times, and the last time is the only time we get heads. So we get 1 out of 5, or 0.2 for a sample proportion. So the table that I have here shows all of the different possibilities that can happen when you flip a coin 5 times. So I show it in the table, and then we created a histogram. And you can see the histogram of all of these p-hats is unimodal and symmetric, and therefore can be approximated with a normal curve. Also, if you put all of these p-hats in and do a 1var stats command, you're going to get a mean of 0.5 and a standard deviation of 0.2236. So I want you to see that the mean of all of the p-hats is 0.5. That was the population proportion. But none of the p-hats actually give us 0.5. Look at the table. Not a single sample proportion is the quote-unquote correct answer. But when we take the average of all of these sample proportions, we get the population proportion, 0.5. The standard deviation also has a pattern to it, which I'll talk about in a second. So now what happens if we increase the sample size from 5 to 50, and we toss the coin 50 times each time? So obviously I could not include a table of all of the different possibilities that can happen when you flip a coin 50 times. But what you're going to see when that happens is that you still get a unimodal and symmetric distribution, and this time it can be even better approximated with a normal curve. We also get a mean of all of these p-hats to again be 0.5, the population proportion. The standard deviation is 0.07. I want you to see that the standard deviation is much smaller than the standard deviation when the sample size was 5. When it was 5, the standard deviation was like 0.22 something. And here the standard deviation is 0.07. So what happened was, as the sample size got larger, the distribution got more normal and it got less spread out. So it got even closer to that population proportion. There was less sampling variability when the sample size was large, and that's why the standard deviation is smaller. So this relationship is always going to hold. And I have a slide here so that I can show you the notation and the formulas that are for the sampling distribution of a proportion. So as we've seen from both of the examples, the mean of all of the proportions, the sample proportions, is the population proportion. The standard deviation is actually the square root of PQ over N. I use Q. Sometimes the textbook, instead of using Q, always uses 1 minus P. So if you remember back to when we talked about discrete random variables, P was the proportion of successes and Q was the proportion of failures. So basically P and Q are complements of each other. So the pattern for the standard deviation is the square root of PQ over N. I want to just make a little note here. We had, in this example, we had a population proportion of 0.5, which means it's nowhere close to 0 or 1. And that's why the sample size of n equals 5 gave us a nice symmetric, fairly normal distribution. But when we have a population proportion that's closer to 0 or closer to 1, we need a larger sample size. So people much smarter than me figured out that a normal curve is appropriate whenever n times p or n times q are both greater than or equal to 10. So this is called a condition of this sampling distribution, and we'll get into more assumptions and conditions in a little bit. So this is the formal theorem. It's the central limit theorem for proportions. And it basically says that as long as that condition holds, that n times p is greater than or equal to 10 and n times q is greater than or equal to 10, that the mean of the sample proportions is the population proportion, and the standard deviation of the sample proportions is the square root of PQ over N, and that they will be best approximated with a normal curve. We know that as the sample size gets larger, the sampling distribution will become more normal and will become narrower. There will be less sampling deviation. So the assumptions and conditions in order to use a normal model to approximate the sampling distribution. First, we want to be able to assume that the individuals within the sample are independent of each other, that none of the individuals have a relationship with each other. This is not actually something that we can check. We want to be able to assume it. So we check two other conditions instead. First, we want to make sure that the sample is random. So we learned all about randomization in chapters 10 and 11. So basically, if we're talking about an experiment, we need to know that the subjects were randomly assigned to treatment groups. And if we're talking about surveys, that there was a random sampling method that was used. The other condition is the 10% condition. And this one's kind of weird. So basically, we want to make sure that the sample size is not too large. And the reason I say that's weird is because typically we'd want just like as big of a sample as we can get, right? The bigger the sample, the more individuals within the sample, you'd think the better approximation it would be. But it turns out that if it starts to get too big, then you can't follow through with this independence assumption. And there's some other problems with it as well that are far beyond this course. So the 10% condition says that the sample size can't be more than 10% of the population size. So then if we have a random sample and a sample that meets this 10% condition, then it's safe for us to assume that the individuals within the sample are independent. And then our last condition is this n times p is greater than or equal to 10 and n times q is greater than or equal to 10. And they call this the success-failure condition. All right, so let's do a couple of examples. So it says the soft drink cups at a certain fast food restaurant have tickets attached to them. Customers peel off the tickets to see whether they win a prize. The proportion of tickets are winners is P equal to 0.25. So notice we know the population proportion, right? It's 0.25. A total of n equal to 70 people, so that's our sample size, n equals 70, people purchase soft drinks during a randomly chosen hour and day. Let P hat be the proportion that win a prize. So before we continue with this example, we want to check the assumptions and conditions. So it told us that the sample was random, and we're going to assume that if 70 customers go to this restaurant in a random hour and day, that would be less than 10% of all of the customers that go to this restaurant. Which means that we can then assume that the individuals within the sample are independent. And then finally, if we take n times p, so our n is 70 and our p is 0.25, if we multiply those, we're going to get 17.5. That's greater than or equal to 10. And n times q, which would be 70 times 0.75, is going to be 52.5. And so both of those are greater than or equal to 10. So we've met that success-failure condition. So we want to then describe the sampling distribution for P hat. So we know then that the mean of all the P hats is the population proportion, which we're told in the problem is 0.25. And we know that then that the standard deviation is going to be the square root of PQ over N, which in this case is the square root of 0.25 times 0.75 over our N, which is 70. And this, lost my little cheat sheet here. There it is 0.0518, which means that because the conditions are met, we have a normal distribution with a mean of 0.25 and a standard deviation of 0.0518. This is how we describe the sampling distribution. We did a lot of this back in Chapter 5, just by the way. So speaking of Chapter 5, we also learned in Chapter 5 the two commands in our calculator when working with a normal model, and they were the normal CDF command and the inverse norm command. So you're going to want to make sure to use those commands when you're asked about the probability of observing certain sample proportions. So I have the same problem written above and what we found on the last page. And we want to do these three problems here. So the first one says, what is the probability that a sample proportion is less than 0.18? So remember that the mean of all the sample proportions is the population proportion. That's that 0.25. So that's right in the center. We're looking for the probability of observing a sample proportion that is 0.18 or less. So we're looking for this area under the curve. And again, remember back to Chapter 5. To do this, we do the normal CDF command. The first value is the lower bound of this region, which in this case is negative infinity. So remember, we used a bunch of negative 9s. And the upper bound is the 0.18. And then we put the mean and the standard deviation. So we have the mean and the standard deviation. And we throw that into our calculator, and we get 0.0883. Remember, this is a probability, so it's going to be a positive value between 0 and 1. The next question says, what's the probability that the sample proportion is greater than 0.3? So again, our mean is 0.25, so now we're looking for the probability of being greater than 0.3. So we're looking for the area under that part of the curve. Again, it's the same normal CDF command, but in this case, the lower bound of this region is the value 0.3. The upper bound is positive infinity. Remember, we used a bunch of positive 9s. And we have 0.25 as the mean and 0.0518 as the standard deviation. And this gives us a probability of 0.1672. And then finally, the last question says, what is the cutoff value for the top 5% of sample proportions? So this is kind of the opposite question. So again, we know 0.25 is in the center. We want to know if this is the top 5%, then what is this cutoff value for the sample proportions? And so instead of using the normal CDF command, remember we use the inverse norm command. Also remember that if you have the newer calculator, this is there's a different setup than if you have an older version of the calculator. So if you have a new version of the calculator, you can just use the 5%, which is 0.05, use the mean and the standard deviation, and then you choose right, since it's a right region. And you will get 0.335. Notice that this answer is not a probability. This is a sample proportion. So we're saying that if a sample proportion of 0.335 is going to be the cutoff for the top 5% of sample proportions, right? So if we were doing this survey and we got a sample proportion of 0.9, we would know something's wrong, since 0.335 is in the top 5%. If you have an older calculator, remember that the inverse norm only works for the left, that says norm, there we go, for the left area. So you're using the lower region, but it's going to have the same cutoff value. So instead of using the 0.05, you're going to use 0.95 with the mean and the standard deviation. And you will still get the same answer of 0.335. If you need a brush up on these, go back to the slides for chapter 5. All right, one more example here for this video. It says approximately 60% of eligible voters voted in the 2016 U.S. presidential election. If a random sample of 88 eligible voters were polled, would it be unusual if less than half of them had voted? So notice that I'm talking about a sample of 88 voters, which means the first thing we want to do is figure out the sampling distribution for this, so that we can then talk about the probability of observing a sample proportion of 0.5 or less, 50% or less. So let's check the assumptions and conditions. So we've got a random sample. It says it right in the problem. 88 is definitely less than 10% of the millions of voters that voted in the 2016 presidential election, which means that it's safe for us to assume that the individuals in the sample are independent. And then finally, if we do that success-failure condition, n times p gets us 52.8, and n times q gets us 35.2. Both of these are greater than 10, so that condition has been met. So then that means that we can approximate this sampling distribution using the normal curve, and that the mean of the sample proportions is going to be the population proportion, which is 0.6. And the standard deviation of all of the sample proportions is going to be the square root of PQ over N, which is the square root of 0.6 times 0.4 over 88, which gets us 0.052. We want to know if it's unusual if less than half of this sample had voted, meaning what's the probability of observing a p hat that's 50% or less? So we would do the normal CDF command. 50% or less, that means we're going from negative infinity to a proportion of 0.5 with a mean of 0.6 and a standard deviation of 0.052. And when we put this in the calculator, we get 0.027. And remember from a previous video, we talked about what it means to be unusual. And we said that if the probability is less than 5%, that would be considered unusual. And this probability is 2.7%. So we would say, yes, this is unusual. Is less than 5%. So this would be unusual.